Okay. Now, when it comes to model evaluation, we need to understand why we need model evaluation. So you might have 100 models, but how do we say that one model is the best? How do you give to your employer and say, okay, this is the model that you should use? So to understand that, we need a way to evaluate our models. So we have different methods to evaluate, and I'll be talking about few of them. So mean square error is one. Mean square error is, it measures how much your model deviates from the actual value. So it takes the y1 and it takes the difference between the actual value and the predicted value. We square it and we take the mean. So that's what we mean by mean square error. And then we have root mean square error. That is the one that we will be using for the datathon as well. So basically, it's just the square root of the mean square error. And root mean square error, it becomes useful than mean square error, because sometimes mean square error can be really huge because we take a square here, and root mean square error, it takes it to the values that we are using. So it takes the scale down to the values of y. Yeah, so that's one evaluation measure. And then we have mean absolute error. It's also similar to mean square error, but it takes the absolute value of the error instead of the square. So what happens with this is we are not penalizing for the large deviations. So if your model, if you don't want to penalize the large deviations, you can go ahead with mean absolute error. And there's R squared and adjusted R squared that we usually use. So R squared, it measures the amount of variability that is explained by your model. And the equation for R squared is here. And when it comes to adjusted R squared, it penalizes when you have many number of variables. So sometimes you don't really need all those variables to predict it. The adjusted R squared, it penalizes these unnecessary variables. So these are few evaluation methods, and I'll move back to Colab and I'll show you how to implement that. Okay. Can everyone see Colab again?
Yeah, yes, we can see.
Okay, right. So mean square error and root mean square error. Let's first do an in-sample prediction. So we'll be predicting on our training data itself, and we predict using the predict function, and we call it as y hat. So mean square error, we use the stat models, tools, and we use evaluation measure, MSE, that's the mean square error. And we give our actual value, that's the DF1 temperature, and y hat is the one that we predict. For root mean square error, it's the same module, but we have to use the RMSE tool, right? Okay, so now we can print mean square error and RMSE of the simple linear regression we put, and we have a mean square error of 38.9 and RMSE of 6.24. And when it comes to mean absolute error, it's similar. We have to use a similar code, but we have to use mean abs. So let's see our mean absolute error. It's 4.95. Okay, so for R squared, we can use result.R squared, or we can use result.R squared adjusted and simply get the two values. So both are the same because we only have one variable and there is no adjustment. So it's 0.880 for both the cases. And that's what we got from here as well. So if you use stat model summary, you can see it without doing this code. Okay, so Now we did a model evaluation, but is what we did correct? So we basically evaluated our model based on the data that we used for training. But is that what we actually need? We need to predict on something that we haven't seen before. So we need to split our data for training and testing. So let's prepare our data for like a proper modeling scenario with train and test split. So like in the previous session, I have filtered out this data, temperature average, dew point average. I haven't considered events. I use all the other 7 variables that the previous speaker discussed, and I call it to a data frame as df2. I get a copy of the data. And I don't really need to go into details on data cleaning because we covered it earlier. And this is the cleaning data, the function that we use. So we can efficiently clean the data for all the columns. So I'll run over that. And finally, this is the data frame that I will be using, and temperature average will be my y, and all other variables will be my x variables. I removed the N99 values, and let's just visualize how our variables look like. So I always like to visualize what it looks like to get the feel of the data. And I'll be using the px.scatter matrix for the visualization. So you can basically pass the data frame, just pass the data frame, and you can adjust the height and the width accordingly to see what the data looks like. So as you see, we see the relationship between the dew point average and temperature here, and then the third variable is the humidity and temperature. So we basically see how our data is distributed, pairwise distributions. Okay, so now let's define our x and y variables. So our y is going to be temperature, and our x is everything else other than temperature. And we define our y, x, and y, and here we see the data frame of our x variables. Right, so now we are going to split our data, and to split the data, we use the scalar and model selection. From that, we import the train test split. So we have the x train, x test, and y train and y test. We use the train test split, and then we pass our x and y data sets, and we give the test size to 0.25, and we put the random state 42, because when we put random state as something, then everyone can repeat the same value, so repeat it and get the same values. So I get the test size of 25%. Usually you can take it between 20 to 30, that's the usual standard. So you can examine the data, and for this one, we think 25% sounds good. So we have 980 data points for training, and for testing, we'll be using 327.